right, here we are in section P.3, which is on radicals and rational exponents. So a little bit kind of merging with what we did in section P.2 with exponents. So again, evolving and building upon our concepts. So it's very, very important for you to master what we've done before so we can kind of move forward. So from our previous section, we know that the square of 3 and negative 3 is the number 9. Here. Now, the reverse or the inverse operation of squaring a number. So, inverse or the reverse going backwards. If I start with 9, how can I get to 3 and negative 3? That is what we refer to in math as the square root function or operation, I guess you could call it as well. So, if I say I have 9, then I want to use this symbol, sort of kind of looks like a check mark. Then that would equal 3, because we're going to ask ourselves, what do I multiply 9 by itself 2 times in order to get that number? So we would multiply 3 times 3 to get that number. Now, also, if I did to get negative 3, then I would end up having to have a negative in front of that square root to give me the negative square root of 9, which is negative 3. So, in the end, if I look at kind of some terms here, with my square root, there is an in out front, which we refer to as the index. Now, you say, well, there's not really a number in these ones that we looked at previously. If there is not a number, it is understood to be a 2, but we don't write the 2. So if it's like we had, like x, y squared in variables, we don't write the 1 as the power of x. So it's something like that. It's understood to be a 2. Then, if I put a underneath there, this is what we refer to as the radicand, what is underneath the square root, and this is just the radical sign. So there's some terminology for you in order to get used to these radicals. So we call the principal square root. It's kind of actually this first one that I did here for you. Of a number, it's called the positive square root. I messed up. Let me erase that. Not the principal, but the positive square root of, get my line thickness. It's called the principal square root. Sorry. Many times one can ask the question, what do I square to get the number underneath the radical sign to get the answer to a square root problem? So let's evolve into a couple of these problems here and see what we get. If I look at this first example, the square root of 81, let's ask ourselves that question. What do I square to get the number underneath that radical sign, or 81? Or what times what, which is the same, gives me 81? That is 9. That's your answer. Nothing else. Not a radical 9. It is 9. What is the square root of 16? So what times what is 16? Well, that is 4. But I do have a negative out front, so this full answer here would end up being negative 4. Now, there is something here with a fraction. I know people kind of freak out with fractions, but remember, we're looking at what times what gives us the same number multiplied by itself to get 1/9. Well, a trick here is going to be look at each of them individually. What times what gives me 1? That's going to be a 1. And what times what gives me 9? That gives me a 3. So collectively, 1/3 times 1/3 is 1/9, but we will see a property later on how I can definitely split that. Fourth example here. Notice that we have a square root, but I have a sum underneath there. We're going to treat kind of the square root as a grouping symbol. So you need to simplify by what's underneath there first, the way it's written here, and then take the square root. So if I add 36 and 64, I do get 100. So then we ask ourselves, what times what gives me 100? Well, the answer is 10. So the square root of 100 is 10, not the square root of 10. It is just 10. Now let's look at these. This is different than here. Here, I need to do these individually and add, whereas this place, I added first and then did the square root. So what times what gives me 36? The answer is 6. I want to add to that what is the square root of 64. What number times itself is 64? The answer is 8. When I put those together with the sum, the final answer is 14. Now, in order to do square roots, you want to make sure that you are very proficient in looking at perfect squares. So, a number that is a square of a rational number is what we refer to as a perfect square. And it is very, very important to be able to recognize these. So, we're going to list the first 12 perfect squares. So, if I do 1 squared, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 squared is 25, 6 squared, 6 times 6 is 36, 7 squared is 49, 8 squared, we just saw, is 64, 9 squared is 81, 10 squared is 100. When we get to 11 times 11, that's going to give me 121, and 12 squared gives me 144. So these numbers are very, very important when we're getting ready to do what we are going to next, which is going to be simplifying square roots, because not all square roots are going to be a perfect square. All right. These will be helpful when we get numbers under a radical that are not perfect squares. We can use these to simplify radicals. First, let's look at a couple radical properties which are true. So this is going to kind of get in what I used up there with that 1/9. First one is called the product rule. So if I have the square root of two things that are multiplied together underneath, that means this rule tells me I can separate them individually, square root them, and then multiply. And that's going to be very, very helpful when simplifying radicals. The one that I used up top verbally was if I had two things that are divided and have a fraction underneath the square root, then you can look at square rooting each one of those individually. And again, that's going to be very, very helpful for us. Now, a square root is simplified when its radicand, or the number underneath the square root, has no factors other than 1 that are perfect squares. So what does that mean? If I look at this first problem, square root of 75. First off, that's not one of my perfect squares that are listed here, but I do have one of these numbers that is a factor of 75 that I can break it up as two individual radicals. Now, thinking about 75, you can do factor trees, like split it up, and that's 3 and 25. Then you can split it up as 5 and 5, which some people might have done that previously, but I like to just look at the perfect squared list and see which one of those will actually go into 75 evenly. And I'm hoping you're honing in on this guy right here, number 25, because I can split that as 25 times 3. So 3 is kind of like the leftover. 25 is my perfect square, and so in order for it to be simplified, I can't have any perfect squares under that radical still. So what is the square root of 25? Well, what times what gives me 25? It is 5, and then I'm just going to rewrite that leftover. And this is what we call a simplified radical. Now, let's look at the square root of 32. Which of these numbers will go evenly into 32? Well, obviously, you're not going to look from here and beyond because 32 lies in between here. So look below. Now, the first one that you might see is 4. So I think about splitting this as 4 times 8. So, if this I think is my only perfect square, let's look to this number and make sure there's not a perfect square in there that's a factor. So again, will one of these numbers go evenly into 8? I'm hoping that you're honing in on this one again. There is another factor of 4. So, there's actually two factors of 4, which means if I multiply 4 times 4, I get 16, which is actually the highest or the biggest perfect square in 32 that will work. So you can do it individually and do the 4s a couple times, but I will tell you it's much easier if you go ahead and get that highest power or the highest number going into 32 first. So I'm going to think about that 16. 32 split up is 16 times 2. 2 is a number that doesn't have a perfect square in it, so we're good. It's best I can write is that square root of 2. And then the square root of 16, what times what is 16? and that answer is 4. So remember that square root of 2 is an irrational number from when we talked in section 1, and so that one will never break down. All right, let's look at 600, get a little bit bigger. Which one of these will actually go into 600? Well, hopefully you kind of recognize the 0 zeros there. This I can split as the square root of 100 times the square root of 6. Again, breaking them apart individually. 6 does not have a factor that is a perfect square. None of those perfect squares go into 6 evenly. Square root 100 to give me 10, and the square root of 6, and that's my final answer. Now, what about if variables are involved? When we look at variables, we're now looking at their power. And we're not looking at necessarily these numbers that are perfect squares to go into it. We are wanting to hone in on even-powered variables. They are going to be perfect squares. So, if they are not evens, then you're going to have some leftover within your radical. Okay, so let's look what we have here on this. Now, if I look at this guy here, the square root of 64 x to the 4th. I hopefully can recognize 64 as a perfect square. If I look at x to the 4th, what times what gives me x to the 4th? Well, it has to be something that's the same. So it goes back to, remember, when adding those exponents. So it is, if I had x squared times x squared, that would give me x to the 4th. They are exactly the same, so that would be the square root. An easy way to figure out the new power is to take this power inside and divide it by the index. Remember, it's an invisible 2 out front. So 64 gives me the 8 when I square root it. And when I take the power over the index, that gets me the new power, okay? So I get x squared. So you can always check your answer. If you square this, do you get back what's underneath there? And I hope you say yes. So 8 times 8 is 64. X squared times x squared is x to the 4th. Now, look at this guy here. 27 is not on our list of perfect squares. This is an odd power, and this is an odd power. So neither one are perfect squares. But there is a perfect square up to that odd power. So you're wanting to hone in on the highest even number up to that odd. So I'm going to use my product rule, and I'm going to break this into 2 different square roots. The first one being perfect squares, and this being our leftover. So if I look at 27, which one of those perfect squares goes into 27? 1, 4, 9, 16, 25, and I stop there. It can't go above 27. Hopefully you're telling me and saying 9 is the perfect square that goes into that. So 9 times what is 27? Well, that's a 3, so that needs to be in the leftover. X to the 5th is not a perfect square because I can't divide 5 by the 2 evenly. So what is the highest even up to x to the 5th? Well, it is an x to the 4th. Now, I still need to have that extra x, but it's going to be leftover, so I need it back here. Highest perfect square on my variables up to y to the 3rd. Well, what's the highest even up to 3? It is a y squared, but I need 3 of them total, therefore one of them has to go in the leftover spot. So, if I have this, we can now square root the front and then rewrite the leftover. So the square root of 9, what times what is 9? It is a 3. Take your power, divide by the invisible 2. So we would get x squared. Y to the 2 divided by 2 gives me a 1. You don't have to write that, but I do need to rewrite my 3xy. And that's my final answer. Okay? Now, let's go backwards with our product rule and put this together and then find the square root. So if I multiply to get all underneath one square root, I get 18x squared. Well, that x squared is nice because that's going to be a perfect square, but 18 is not. So I'm going to come down here and do my perfect square times what's left over. So of 1, 4, 9, 16, which goes into 18, it is a 9 times the 2 gives me the 18. And we already discussed that x squared is a perfect square. So the square root of 9 gives me 3. Power divided by the index out front gives me just x to the 1st. You don't have to write that. But then I have the square root of 2 as my leftover. and that would be our answer. Okay? All right. Now let's work with the quotient rule. Here I have a fraction that I can very nicely take the square root of 100 over the square root of 9. And this is a pretty easy one because they both come out very nicely. What's the square root of 100? Well, we square 10 to get 100, and we square a 3 to get 9. Therefore, that's my answer as 10/3. Now, when I do this guy, unfortunately, 50 is not so nice. It is not a perfect square, but 9 is. So, I need to think about 50 and figure out what is the perfect square in 50 that will go into that. So, 1, 4, 9, 16, 25, ding, ding, ding. 25 should be that times the 2. Again, that makes the 50. We're just breaking it up as factors. I'm going to go ahead and square root the 9 to give me a 3. And now all I have to do is simplify the numerator. So I'm going to have a square root of 25, which is 5, square roots of 2 all over 3. Now, these two numbers out front, without radicals, if you were able to cancel things, like for instance, if I had a 6 square root of 2 all over 3, I could cancel that and make that a 2 root 2 is my final answer. So make sure you check that to see if you can simplify further, okay? All right, so this is our final answer here. The last one for this page, we have two things that are being divided, but just like we were able to put things together here, since each of those have a radical, I can actually put them all underneath one square root. Now, why is that helpful? Hopefully you notice that there is a common 2 between 150 and 2, and there's some x's I can cancel, actually just one x that I can cancel. So if I take 2 into 50, that gives me a 75, and this x into that x gives me 4 left over in the top. So everything's gone out of the bottom. Technically there are 1's, but 1's not going to make a difference. So what I get down to now is the square root of 75x to the 4th. And this is much nicer to work with than that fraction right there. So again, I'm going to do perfect squares times what's left over. 75 has a factor of, what's perfect square? 1, 4, 9, 16, 25. Ding, ding, ding. We've seen that one before. 25 times 3. And since 4 is an even power, it is a perfect square. So now simplify this part. Gives me a 5x to the 2nd when I divide power over root. And then I have the leftover of the square root of 3, making that my final answer. Okay? All right, very good. Let's check out what we have coming up next, which is adding and subtracting radicals. So, adding and subtracting radicals, going back to, I believe it was section 1, where we started looking at simplifying like terms. It is just like that. So if I wanted to say 2x plus 5x, that's going to give me 7x. So I didn't change the label, I just changed the number out front. So in order to add these things together, the radical and the index have to be exactly the same. So if I have 8 apples plus 7 apples, I get 15 apples. Well, here I have 8 square roots of 11 plus 7 square roots of 11 gives me 15 square roots of 11. That radical does not change again. Here I have a 1 square root of 5y minus 16 square roots of 5y. Each of these are exactly the same. Therefore, I can combine the 1 minus the 16 and get a negative 15 square roots of 5y. And that'll be my answer. And lastly, on these examples, notice that I have one radical that's kind of the black sheep of the family. This does not match the square root of 5. So unfortunately, I can't do anything with that but rewrite it. But I can combine these two with the square roots of 5. So a positive 2 minus 4 gives me a negative 2. Check it on your calculator if you need to. Square roots of 5, and then I'm going to just rewrite that 3 square roots of 7 because there's nothing I can do with that. Okay? Now, of course, things aren't going to be as easy as those 3 problems because then we turn to problems like this example here, 5 square roots of 27 plus square roots of 12, that I have to simplify first and then combine like terms, okay? So let's see if we can do that. I'm going to do exactly what we were doing on the other side, and I'm going to break it as, and hopefully you'll get used to breaking it in your mind, and then just skipping a step and not have to writing it. 27 has a perfect square of a 9 times a 3, and let's go ahead and do the 12 while we're at it. 1, 4, 9, then when it gets to 16, that's too much, so one of those has to go into 12, which is 4 times 3. So now I'm going to do this piece right here. Now that gives me a 3. But notice I have a 5 out front. Can't forget about that 5 because it's 5 times that radical. So I have to do the 5 times the 3 and give me a 15 square roots of 3, because here's my leftover, plus the square root of 4 is a 2 square roots of 3 after I rewrite that. And now, can I combine them together? Absolutely, because there's both square roots of 3. So 15 root 3 plus 2 root 3 gives me 17 root 3, and that would be my final answer. Okay, let's do one with variables. Still, I have these numbers up front 6 times, 4 times that, so I have 6. Now, what is the perfect square in 18? And what is the perfect square in 8 and what's left over? Okay, so let's look at 18. 1, 4, 9, 16. I'm going to make that a 9 times a 2. Now, is x a perfect square? Hope you're shaking your head no, because it is not. I just need to leave that in the leftover part. Moving on to the 8. If I simplify 8, 1, 4, 9. Whoop, back up. Does 4 go into 8? Most definitely. 2 times, so 4 times 2 gives me 8. Again, x is not a perfect square, therefore it is in the leftover. So let's see what we get here. This gives me a 3. So if I change that to a 3, I need to multiply here to give me an 18 square roots of 2x. Subtract, this gives me a 2. That I want to multiply by that 4 gives me an 8 square roots of 2x. So change the number out front, keep the label. 18 root 2x minus 8 root 2x gives me a 10 square root of 2x. And that's our answer. So there you go for adding and subtracting. That's what we have. So again, we're going to kind of go through all operations. We're going to now lead into multiplication. And, oops, sorry. We're not going to do multiplication just yet. We're doing some division here of those. So, rationalizing denominators. One rule for simplifying radicals is that a radical cannot be in the denominator. So if I read what I have here, in order for a radical expression to be simplified, one cannot have a perfect square under the radical. That's what we were doing up here to get rid of that perfect square. But another rule to simplifying radicals is that a radical cannot be left in the denominator. So the process that we use to get the radical out of the denominator is called rationalizing the denominator, okay? So here's how you do it with square roots. And it's pretty easy when it's square roots. All you have to do is multiply the top and bottom by the simplified radical in the bottom, okay? So what do I mean by that? This radical here is simplified. There's nothing I can pull out as a factor of 3 because I only have 1 and 3. 1, 4, 9, 16, 25, all those perfect squares are not a factor of 3. So I'm going to multiply the top and bottom by the radical that's in the bottom that's simplified. Now, why can I do that? Hopefully you would agree that the square root of 3 over the square root of 3 is 1. So when I multiply 1 by anything, it doesn't change the value. It's just going to change the way it looks. So, if I do that, and again, it's going to be easy. You don't have to really think about it. You just multiply by the radical that's in the bottom. I'm going to simplify the top here as 5 square roots of 3. And this is where I want you to get good at squaring a radical. If I do the square root of 3 times the square root of 3, technically, that is the square root of 9. Which, in turn, what number times itself gives me 9? Well, it is 3. So, notice that if I multiply a radical by itself, what I kick out is the number underneath. So, root 3 times root 3 is 3. Root 5 times root 5 is 5. Root 11 times root 11 is 11. okay, with no radical whatsoever. Therefore, my final answer for this problem is 5 root 3 over 3. Again, make sure you check to make sure you can't cancel these out front. Now, you cannot cancel these because this one has a radical and this one does not. Okay? Let's look at this next problem. 8 over the square root of 2. I can't have a radical in the denominator, so I'm going to rationalize the denominator by multiplying top and bottom by that radical. So, the top we can just put together is 8 root 2 because you can't combine one radical and a whole number. But root 2 times root 2, technically root 4, which kicks out a 2. But remember, root 2 times root 2 is just 2 without a radical. Now here, watch right here, notice that 2 can go into that 8 4 times, therefore making 4 square roots of 2 my final answer. Okay? Now, the last problem is just a little bit different just because it has a radical that needs to be simplified. So if I look at 12, 12 has a perfect square in it. We've already looked at 12 one time before, up here I believe on this problem. And so, what's the perfect square in 12? It is 4 times 3. So I'm going to go ahead and rewrite this problem as 6 over the square root of 4 is 2 square roots of 3. Now, one of two things can happen here. You can multiply now by root 3 and root 3 top and bottom. I would choose to do this canceling. The more you simplify to begin with, the easier it is going to be in the end. So I'm going to cancel that 2 into that 6 and leave me with a 3 on top. So technically, my problem comes down to this. 3 over the square root of 3. So I'm going to multiply top and bottom by that radical. I'm going to bring you down here. The best I can write the top is 3 radical 3 all over. Now here's what we just did back over here. What is root 3 times root 3? Well, it is just 3. Can I cancel lots of 3's here? Can I cancel these two? No. One has a radical, one does not. Can I cancel these 3's? Absolutely. Mark those out as 1 and 1. The ones basically kind of go away, so our final answer on this one is the square root of 3. Okay? All right. Moving right along here. If you have a problem or something or need to review something, make sure you pause the video and go back and re-listen to it. Hopefully it'll sink in. All right, so that's when I have a radical that's in a bottom by itself. What happens when I end up having some pluses and minuses? Well, it's not as easy. That's where in math we have to look and talk about conjugates. If the denominator has a sum or difference, then we will need to determine the conjugate of the bottom and multiply top and bottom by that expression. So let me tell you what a conjugate is. A conjugate basically is that you have to keep the first number the same and this sign between is changed. Okay? Maybe I should change that to one of them being a negative. Let's do that. I'm going to make that one a negative here on the fly. Make that a minus. And so it says that the conjugate of 3 plus root 5 is, well, I'm going to keep the 3, but I'm going to change that to a minus and keep the root 5. So the middle sign changes. If I have the expression root 2 minus root 3, then I'm going to have root 2 plus root 3. If I have negative 3 plus root 7, again, this doesn't change. That stays the same, and I change the middle sign as negative 3 minus root 7. And that's going to be very helpful for us whenever we need to rationalize our denominators for these fractions. Now, in order to do it, we got to give you a rule because multiplying our polynomials hasn't happened yet. So I'm going to give you this rule that if I multiply two things that are exactly alike except for the sign, and again, we'll get into more of this later, then there is kind of a shortcut or a formula we can use to get that. This times this, which would be if I were to multiply this times this and this times this, is going to be found by taking the first term, A, and squaring it, and subtracting the second term, B, and squaring it. We'll refer to this later as the difference of squares. Okay, but for now, we're going to use it to rationalize using conjugates. So, we're going to multiply top and bottom by the conjugate of the denominator. So that conjugate, if I have root 3 minus 1, is going to be root 3 plus 1. So again, I'm multiplying by 1. So I have to multiply top and bottom by the exact same answer. I'm going to put these together as 6 square roots of 3 plus 1 all over. Now, using my formula here, I need to square the first term. So I need to do root 3 squared minus the second term squared. And that I need to now simplify. So again, make sure you follow step by step so that you know how to do these. All right, so the top I just rewrote. The bottom we need to figure out what that is. So I'm going to have 6 square roots of 3 plus 1 all over. Now, what is root 3 times root 3? It is just 3. You can go through the motion of making it square root of 9 and then taking the square root, which still gives you 3. 1 squared is a 1. And so this becomes a 2. I'm saving some writing here. So when I have that 2 in the bottom, notice it's without radical. This is without radical, so we can definitely simplify that by canceling those things out. Final answer here would be 3 times root 3 plus 1. That's one answer. But you could also use the distributive property to give another answer. So without parentheses, 3 times root 3 is 3 root 3. 3 times 1 is a plus 3. So either one of these answers would be acceptable for that. Okay? All right, let's look at this last one on these for conjugates. I have a sum in the bottom, so that means it's not just as easy as to multiply by one radical. We have to multiply by 2. We have to determine the conjugate of root 7 plus root 3. Well, let's change the middle sign, and that becomes root 7 minus root 3. And what I do to the bottom, I must do to the top, because that is really 1. And this time again, I'm going to just keep the 11 outside. You don't have to bring that in unless it prompts you on your online stuff to bring that in. Hopefully it'll grade either one. All right, so the bottom, again, we have to square the first term minus the square of the second term. That will get us what the product is in the denominator. So what is the square root of 7 squared? Well, square root of 7 times square root of 7 is just 7. Minus the square root of 3 times the square root of 3. Go through the motions if you want. Square root of 9, which is 3. Or root 3 times root 3 is just 3. So a 7 minus 3 is going to be a 4. But notice that 4 won't go into this 11, and it definitely won't go in with those radicals. So I'm just going to rewrite this as the final answer. So don't force things to cancel, because all the time it does not always happen. Okay? All right. Let's do in some cube root stuff, and we'll get some fractional exponents and be done with this section. So not only are square roots important in math, but also when we look at cube roots, it's going to be helpful when simplifying cube roots within math. And of course we have fourth roots and fifth roots, which is, taking things to the fourth power, the fifth power, etc. But we normally don't usually use those. So I'm going to give us a list of the first 6 perfect cubes. And so remember, cubing means that I have 1 to the third power, which means 1 times 1 times 1, which is 1. 2 to the third power, not 2 times 3, but 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. If I do that with 3, I get 27. 4 cubed is going to be 64. Then I have 125, and then we have 216. So just like our numbers of our perfect squares, these are going to be very important to us when we're looking for perfect cubes. Okay? What do I mean by that? Let's look at these here and see if we can simplify them when now I have an index out front. Oop, I got a 4 in there too. We'll have to think about that one. Simplify with cube roots. So now instead of asking ourselves, what do we multiply by itself twice to get that number underneath, we're wanting to know, what do I multiply by itself 3 times in order to get negative 125 in this first instance? So, what times what times what is 125? Going back to our previous page, and maybe should have put it on the same page. 1, 2, 3, 4, 5 cubed is 125. Therefore, in order to get that negative, remember 3 times, a negative times a negative times a negative is a negative. Therefore, negative 5 is our answer. Now, we could never do that with a square root and have a negative underneath. That's a non-real number, okay? Which actually we'll get to in just a second. So ask yourself, what times what times what is 8? And hopefully you kick back with a 2. 2 times 2 times 2 is 8. Make sure you're familiar with those first 6 perfect cubes. Now, if I have a fourth root, that means I'm going to multiply a number by itself 4 times to get the number underneath. Well, notice that that number underneath is a negative number. Is it ever possible that if I multiply 4 times 4, or, excuse me, negative 1 times negative 1 times negative 1 times negative 1, 4 times, am I going to get a negative? And the answer is no, because 2 negatives make a positive. So if you have 4 of them, that means you have 2 positives multiplied together, end up being a positive. So this actually is the empty set. So you cannot have an even index and a negative number underneath. That does not work, okay? Now, the last two are going to be helpful whenever we're simplifying like we were doing before. Looking at what's the perfect cubed and what's left over. So if we think about our perfect cubes, I'll just write them up here. 1, 8, 27, 64, 5 is 125, 216, okay? Which one of those will go evenly into 24? And I'm hoping you're telling me it's an 8. So 8 times 3 gives me 24. Now, what times what is 8? The answer for this is 2. That's the perfect cube. And this is going to be my leftover. So 2 cube roots of 3 would be my answer. Now, this one we have a number, but we're going to have to talk about our variables too, okay? So with 250, which one of these will go evenly into 250? And I'm hoping you're honing in right there. So it's going to be a 125 times 2. But we also have some variables here. Now, when we talked about perfect square roots, we were looking for even powers because they go evenly into the index out front, which is 2. Here, when I have a cube root, you're now looking for not even powers, but multiples of 3. So, 5 is not a multiple of 3. If I try to take 5 and divide by 3, I don't get a whole number. So, I need to figure out what is the highest perfect cube up to x to the 5th. Well, what's the highest multiple of 3 up to x to the 5th? And it is just x cubed. So I need 3 x's up front, but there's going to be some left over because I need a total of 5. That means 2 are left over in the back. And if I look at y to the 9th, can I divide 9 evenly by 3? The answer is yes. Ding, ding, ding. It is a multiple of 3, hence it is going to be a perfect cube. And so once I've decided that, here's my perfect cubes. So I need to figure those out. And then this is the leftover that I'm just going to rewrite as part of my answer, okay? So the cube root of 125 we just saw on the first problem over there is 5. Take power, divide by root, just gives me an x. And power, divide by root, gives me a y to the 3rd. And that, ladies and gentlemen, is our final answer. Okay? All right, one more little concept, and then we'll kind of put it together with some law of exponents. And this is fractional exponents. When you get into higher math, sometimes it's much easier to deal with fractional exponents than it is with all these radicals. And so a lot of times in calculus, you'll use fractional exponents and etc. So check out the following 2 rules, which will help us with exponents which have fractions in them. If a represents a real number and n is greater than or equal to 2, is an integer. So it'd actually have to be positive numbers there. And the fraction m over n is a positive rational number. Then we got 2 things going on here. If I have a to the 1 over n, so now my power is a fraction. Think about power over root. That's what I always kind of tell students is power over root, power over root. So meaning this is the power of this base, and this is the root out front. So therefore, that's going to be my index out front, a to the 1st power. I can write it, or in this case, I'm going to choose not to write it. So that is what that's equivalent to. Now, what if you have any other power besides 1? Well, that's when we get a to the m over n. Again, power over root. So the n comes out front, and I get the power inside there. Now, this is perfectly acceptable. But I will tell you, when simplifying these things, that it's much better to take the index first and then take it to the m power. So I'm going to write it like this. Nth root of a to the m. These two are the same. I choose to do this first in operation, okay? So let's see by example what this really means. Okay, I have 25 to the 1/2 power. Again, power over root. So I have a square root. Now again, that one's usually not written. Square root of 25 to the 1st. So normally we like to see it like this. The square root of 25. So what times what gives me 25? The answer is 5. So 25 to the 1/2 is 5. It's the same as the square root of that. Then, here I have a power over root. So just similar to this, now that index is a 3 instead of a 2. Excuse me, the cube root of -8. And so, what times what times what? 3 times gives me -8. Well, 2 times 2 times 2 does that for me. But I also have a negative that I need to bring out front to get the negative underneath. Now we have a negative exponent, which is different than the negative base. So again, power over root. But let's worry about that negative exponent first. Let's remind ourselves what happens to negative exponents. They allow themselves to flip to the bottom. So this actually would become 1 over 27 to the 1/3, making it positive. Okay? Actually, I'm going to write it that way. I'm going to write it 1 over 27 to the 1/3, where the power is just in the bottom. Okay, so this is 1 over 27 to the 1/3, so that we keep on the same notation as we've done. So I'm going to rewrite 1 over. This becomes the cube root of 27 to the 1st power, or just the cube root of 27. So what times what is 27? The answer is 3. So the ultimate answer here is going to be 1/3. Now, let's try a couple where we have a power is not equal to 1, okay? And what I'm going to look at is I'm going to do the root first and then take it to that power. So here I have the cube root of 27 that I want to take to the 4th power. Always simplify first as much as you can, then do the powers. So what is the cube root of 27? What times what is 27? The answer is 3, that I then need to take to the 4th power. So 3 times 3 times 3 times 3, check it in your calculator or multiply it out, your answer would be 81. Now, what about 4 to the 3/2? Again, do the root first and then do the power. So if I take the square root of 4, again, I'm not going to write the 2, you can write the 2 if you want, but then I need to take that to the 3rd power. So the square root of 4 is 2. To the 3rd power gives me an answer of 8. So it's much better. Let's look at this one. I could have done this as 27 to the 4th power and then take the cube root, and that would just be extremely large. 27 to the 4th is huge. So then I would have no idea what the 3rd perfect cube is for that number. So again, do the root first and then take it to the power. All right, our last 2 problems in section 3. We are looking at simplifying these with our laws of exponents, and they have fractions in them. So just like we did in the last section, here I have this and this that I want to put together. So 2 times 5 gives me a 10, but I have 2 bases and 2 powers. So what I want to do is to add those exponents. Just like if I have x squared times x to the 4th, that would be x to the 6th. So I'm going to add those exponents. So I need to take 4/3 plus 1/2. Now, you are more than welcome to use your calculator if you want, but if you don't, these have to have a common denominator, which would be 6. So I need a times by 2 and times by 2, times by 3 and times by 3. So this gives me an 8/6 plus a 3/6. Keep the bottom, change the top. So ultimately, x to the 11/6 is what we would have for that. Okay? Now, this one has 2 things multiplied together with an outside power that must come inside to each one of those. So I get x to the 4/5 to the 5th times y to the 1/2 to the 5th. And so this is different than these guys over here. Here you add those exponents. 1 base to 2 powers is where we multiply. So if I can digress over here, 4/5 times 5 over 1, again, you can use your calculator if you want, but you can also do this in cross cancel and know that my final power here for x is going to be 4. And for my next one, if I have 1/2 times 5 over 1, unfortunately nothing cross cancels. So just go straight across and leave us with y to the 5/2. And that's going to be our final answer. So hopefully you can practice some of these in order to figure out these radicals and these fractional exponents and get used to those.